Hello, students. I have to tell you about something that happened this weekend. So, I had a fantastic weekend. I met some friends at Buffalo Wild Wings. We were enjoying the games this Sunday, and a neutron walked in. And we'd never seen a neutron before. We were completely blown away. But the neutron walked right in. It went up to the bar, and it talked to the bartender and asked how much for a drink. And the bartender, without ever thinking at all, said, "For you, no charge." Now, all right, fine. This didn't really happen, but it's a great way to remember that neutrons have no charge. They're a very important part of the atom. And since we're going to talk about atomic theory, I thought I'd start out with that fun story to get you guys into it. If you want even more of that, keep listening. So, protons, neutrons, and electrons. You guys, I'm sure you've heard these before. So protons, we remember, have a positive charge, and I don't like writing out all of this, protons, neutrons, and electrons every time I want to talk about them. So there's fun, special symbols that were created just for you guys that make life even easier. So protons, they're P+, to remember protons have a positive charge. There's N0, to remember that neutrons have zero charge or no charge or a neutral charge, and electrons are E-. So, subatomic particles. There's electron, proton, and neutron. Just like I said, there's E-, P+, and O. There is a 1- charge on the electron, a 1+ charge on the proton, and neutrons have zero. But let's take special note of the mass here. Now, you see this means basically electrons have 0 AMU, or atomic mass units is what this stands for, and protons and neutrons have the same mass. That's because protons and neutrons are much, much bigger than the electrons. These numbers we haven't really talked about much yet, but 10 to the negative 31, 10 to the negative 27, that's a difference about 2,000 times. Protons are 2,000 times bigger than an electron. So if you were an electron, that would mean that protons are the size of like a giant 747 airplane. So recall this. This is why when we're talking about mass units, we talk in terms of protons and neutrons, not the itty-bitty electrons. So let's talk about the current classroom model of the atom. The nucleus, that is where our protons and our neutrons are. It's the smallest volume, but the largest density. Remember, it's crazy high density. If you remember from that video, that if you wanted to be as dense as the nucleus, you had a 1 foot by 1 foot by 1 foot box, you would need to put in 6.2 billion cars in that box in order to be the same density as the nucleus. And all the electrons are in what's called orbitals, or orbits sometimes. But it's a large volume. They're tiny masses. Remember, they're 2,000 times smaller, and that's where all our negative charges are going to be. So, if an atom were the size of a football stadium, remember from the video, this is Soldier Field. The atom is this big. The nucleus is the size of the marble at the 50-yard line. It's this marble, and it is at the 50-yard line. This is obviously far too large. The nucleus is very, very small compared to everything else. And that's where protons and neutrons would be, right there in our nucleus. And electrons would be like the fans, or the players on the field. They'd be all over. But you'll notice there's a lot of empty space, like after the Bears lose those stands. That's most of what the atom is. It's all empty. But you may wonder why there are protons and neutrons in this nucleus, why the neutrons aren't somewhere else. And that's because neutrons are there to hold the protons together. There's strong positive charges, and they want to be apart. Just like two of the same sides of a magnet want to be apart. But the neutrons act as kind of a glue. They have something called a strong nuclear force, and they hold those protons together. And the bigger the nucleus becomes, the more protons you add, the more neutrons you need in there in order to keep it stable. We'll talk about that more later when we get to the periodic table. And remember, mostly empty space. Some magnetic fields, but mostly empty space comprises most of the atom. And also remember, P+, what are those again? Yep, you're right, those are protons. They're 2,000 times the mass of the electron. So that's why we'll only be talking about, when we're talking atomic mass, we're talking about protons and neutrons. Protons and neutrons, not the electrons. So let's talk about the periodic table. You're going to see the name. Most of you are familiar with this, carbon. You're going to see the atomic number. It's always going to be a whole number, always an integer, because that gives us our number of protons. You're going to be the symbol, because again, scientists don't like writing out carbon every single time, uranium every single time, so they're going to use a symbol, a C, and the average atomic mass is usually a decimal. You're going to see the average atomic mass because there are different isotopes. We're going to talk about that later, but different isotopes, different forms, different masses of the same atom. So because of that, you have an average atomic mass that's not an integer. And then some also have an electronegativity. We will get there eventually, but we're not there. Just know that this extra number is not the atomic number and is not this 4-digit atomic mass. Average atomic mass is electronegativity. The name is the official name given to the element. The symbol is official symbol. Usually it's very similar, but sometimes it's an ancient name, just like PB, lead. It used to be called plumbum, and the first letter is always capitalized. If you write it and it's not capitalized, then you are wrong, and you're going to lose points for it. So make sure you're capitalizing, guys. And the atomic number, that's the number of protons in the nucleus. Later we'll talk about a neutral atom. If it's a neutral atom, then the protons have to equal the number of electrons. So that's usually where you get the number of electrons as well, if you're solving for those. But when we get to ions, that's not always going to be the case. But it's always going to be the atomic number is the number of protons. And that's because the identity of the element is defined by the protons. If you add or subtract protons, then it's a completely different element. So you can't add protons. You can't take away protons. Otherwise, you're going, if you take carbon, you add 2 protons, you now have oxygen. That's the difference between elements. So let's talk about elements versus isotopes. There's an average atomic mass. That is not a whole number. That's what you see on the periodic table. It's a calculated average. And old scientists, they thought all atoms of an element are identical. We now, knowing a lot more about them, know that that's not correct. Atoms of the same element might have different numbers of neutrons, and that's what an isotope is. It's the same atom, it's the same element, it's just got more or less neutrons, so it's an isotope. Isotope meaning different weight, and that difference in weight comes from the neutrons. But in atomic mass, you're going to see in a symbol is the whole number. That's the mass number, not the average atomic mass, the atomic mass number. It is a whole number because we're talking about one individual atom. And also, if you wanted to figure out the number of neutrons, you're going to use the atomic mass and subtract the number of protons, because our nucleus is made up of protons and neutrons. That's the only thing that's going to give us atomic mass. So if we want our neutrons, we take our atomic mass minus the number of protons. So, shorthand notation. If we want to talk about these 2 different isotopes of chlorine, Cl is chlorine. We have chlorine 35 We always talk about both the protons and the neutrons together. And chlorine 36. Chlorine 35 and chlorine 36, which one has more neutrons? Yes, it's going to be chlorine 36. It has one more. So the A is always going to be the mass number. This is going to be the symbol, and Z is going to be the atomic number, and that gives us our number of protons. So if you wanted to tell me the number of neutrons in chlorine 35, you could take the mass number 35 minus the atomic number, which gives us our number of protons, and that equals our number of neutrons. So 35 minus 17, let's see, 35 minus 10, that's 25, minus 10, that's 18 neutrons. 18 neutrons. You should calculate that out yourself in your notes to make sure you can do that. And also, take some time right now to calculate the number of neutrons for chlorine 36. Go ahead and practice right now. I'll wait. All right. You should have gotten 19. If you did not, you need to recheck your answer. All right, so let's try a problem. How many protons are in this element? First of all, what is it? That's right, it's oxygen. So let's talk about the number of protons. Where do we get that? Yes, that's from the whole number, the atomic number. And that gives us, what? Yes, it's 8. You should have 8. How about the number of neutrons? What would we do? Yes. I'm sure this feels like Dora the Explorer. It's meant to be that way. Fill in the answers, guys. The number of neutrons is the atomic mass, so 16.00, minus the number of protons. Where do we get the protons again? Yes, from our whole number, our atomic number, so 16 minus 8. You should have 8 neutrons. And how many electrons? Let's assume a neutral atom. So we have 8 protons. And how many electrons if it's neutral? 8 positives mean we need 8 electrons. So we have 8. 8 here as well. Let's try mercury. This one's a little harder. You may need to get out your math in order to do that. Your calculator. So first, the number of protons, that's an easy one. It's 80. It's 80, absolutely. And our number of neutrons, how would we figure that out? Yes. You take your atomic mass number, and you always want to round to the nearest whole number, So we know what's the nearest whole number for this? Yes, it's 201. 201. And what are we going to subtract? Yes, it's 80. 201 minus 80. 0. Now we're going to borrow. Let's do 1. That is 121. 121 is our number of neutrons. 121 is our number of neutrons. And how many electrons? Is it 121? No, we know it's going to be the same number. Remember, positives and negatives always cancel out. Positives and negatives always cancel out. We have 80 here. So we know we need 80 here. That's how we get our electrons. So I will leave you with some of my favorite isotopes, carbon-12, carbon-13, and carbon-14. I really hope that this was helpful.